So we were at this level. We had we had done our second level of diagonalization, and that's good because it's starting to indicate how this is just going to be something we do over and over again in more and more sophisticated ways. And so omega naught 2 was a function that could accept an input, and we always, when we have a function in this first slot that can accept an input in the second slot, we tell it, go ahead and take that input to do the diagonalization trick. And that, for example, here was omega naught plus 3. Well, that says repeat omega naught plus 2 3 times. And of course, every time you activate omega naught plus 2, it's really encoding repeating omega naught plus 1, and it's going to repeat it many, 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 many times because you're going to repeat it in a number that's the result of a previous F calculation. So what can we do now? We can look at omega naught 3. That's another slightly higher level or next step in the diagonalization story. That's going to be, again, a function that just takes a number and produces one of our new function slash successor gadgets. And its definition is the kth thing in that sequence is just omega naught 2 plus k. And what's that going to be useful for? We're going to put it into the control slot of the f function. We're going to put an n into that. We're going to just use the basic definition that this is going to diagonalize. That resolves as an omega naught 2 plus n, comma n. Okay, so we've taken the omega naught 2, which was incredibly fast growing because it collated together a bunch of these omega naught plus arbitrarily large number. And now we're going to do the same thing to it. We're going to take a bunch of these omega naught 2s and add an n to that. And that, it might look benign, but it really is part of why this is so powerful. What is that? If that's like omega naught 2 plus 100, comma 100, that's going to be iterate omega naught 2 f omega naught 2 plus 99 to the and iterate it 100 times on 100. Okay, then that omega naught 2 plus 99 will be an omega naught 2 plus 98. That'll be defined in terms of omega naught 2 plus 97s, and eventually that will bottom out at this incredibly powerful diagonalizer, and we're going to feed incredibly big inputs into that. Okay, so that's how I'm saying it is. Iterating the omega 2 level diagonalizer many, many times, and every time that gets unpacked, it's going to activate these omega naught level diagonalizers. So we're really getting something where we're getting something out of combining these ideas of successor on top of one of these functions activates a round of recursive iteration, and then they're grounded on these diagonalizers that then unpack a whole new level of recursive diagonal or recursive iteration. I think we can probably define omega naught times 4. Still going to be a sequence. Omega naught 4, you just have to define what it is at any particular natural number. Omega naught 4 of k is going to be omega naught 3 plus k. And so I want to point out something. It really should be, unless this is really misleading, and it's not, the arithmetic works pretty much as you'd expect. That's omega naught doubled and then doubled again, or doubled iteratively. That should look kind of familiar. So let's think about this. Let's just look about not just omega naught, since that's such a simple function, although it's one of our most basic. Let's look at what happens if we have any function, some previously defined function, and we're defining a bunch of them here, that takes a natural number and produces one of these omega 1 gadgets that we've started to fill out a tiny bit of the space of the omega 1 gadgets. And what should doubling be? Okay, doubling that we're going to define, and we're going to see how this fits into a beautiful general theory in a second, or a few minutes. We're going to say doubling of any function is a new function whose kth, whose output given the kth input, or in other words, the kth thing in the sequence, is just alpha plus alpha of k. And that's just a generalization of like the omega naught 2 that we saw. And of course, that's the kind of thing that we could put into the control slot of one of our functions. But I want to step back. We're really seeing some patterns here that we want to identify. We have a version of, remember the first function we ever defined was successor. And we now seem to have a version of that on omega 1. Well, we do, right? We know what it means. We just mark it with a successor mark. We just put a formal +1 on a gadget. And we know that's meaningful because we know how it works in the control slot. So we have a version of successor. We just invented, I just told you, a version of doubling, which is basically iterated successor, although this can get very interesting, this idea of alpha of k. If alpha of k is actually just a number, like in these cases, then it really is just iterated successor. Going to be a little more interesting, and that's what I want to investigate the rest of this video. Okay, and so we want to see in what sense is this definition of doubling really a significantly more powerful and general version of iterated successor, but still really the same thing. It's really iterated successor. Okay. Now it looks like we can double repeatedly. Like we did doubling and then doubling again with omega naught 4. Okay. So that looks like it's a thing, and it doesn't seem like we should have to stop doubling. Okay. So, well, doubling repeatedly, iteratively, an arbitrary number of times, that turned into the E operation, the exponent operation, when applied to ordinary numbers. So are we building a new level, a qualitatively different level of the fast-growing hierarchy that's now taking function gadgets in omega 1 and producing new function gadgets? And yes, that's what we're doing. Okay, so it should be something like E of alpha. We start with a function. We E it, that should produce a new function. It's going to be at least as complicated. Okay, so it's going to be something that still needs to take an integer input and produce a function type gadget. And it should look something like this. The Eization of alpha, when put in input k, should be doubling, but it's a little bit tricky to figure out, well, doubling how many times? Is it k here? And it turns out it's more interesting than that. It's not just going to be k. And so let's look at what we want to do here. So like I said, I was hinting, we're really recapitulating the story of the fast-growing hierarchy, but we're going to do it on the level of these omega 1 gadgets, and then we're going to put those in as control gadgets in the ordinary F level. But I'm going to change the notation to make it more consistent and make it consistent with what Weiner does in this article that I'm really kind of basing this on. So we're going to rename F. This is usually you just see F in most publications about the fast-growing hierarchy, but I'm going to rename it as phi naught. And so phi naught of alpha n is just a new name for F. And that's because we're going to have a phi 1 in a minute, and then a phi 2, and then a phi 3, and phis at all levels. But it'll take a while. So in this case, for phi naught, the kind of input you have in the first slot it's going to be an omega 1 gadget. Now that includes just good old numbers. Remember, numbers, this is just a name for numbers, and that's so f of 0n, f of 1n, 2n, all those are still fine. But the real power came when these were gadgets that involved a combination of function creation and successor creation. But this is just a number, it's an omega naught, this is an omega 1. Now we are going to define phi 1. That's where the input slot itself can be a function. So the thing we're actually working on is more sophisticated. It's one of these functions. So right now, we're going to go back as if we were kind of in the first stages of the F story a few videos ago, and just define what happens when k is the simplest kind of gadget, which is just a number. But eventually, this will go beyond. This will not only go to omega 1, eventually we'll invent omega 2. But it turns out that these guys can be in omega 2, but we're not there yet. Okay, so this is a way to create a new gadget in omega 1. And again, we really want to think of it as just the fast-growing hierarchy in just a more complicated way. And that's why I think this is so pretty. So pretty much the whole point of this new video series is, as the title suggests, just the fast-growing hierarchy as a clever but not weird way of combining iteration, recursion, and diagonalization. Just push that to the max, and you get to a really pretty decent, really high level of huge numbers. Okay, so in other words, phi1 with control argument 0 on a omega 1 gadget is just successor. Just the first thing we ever did to an omega 1 gadget. Phi1 on alpha is going to be this doubling gadget. Okay. And phi1 on with control argument 2, it should be, well, take alpha, and it really should be take alpha and double it alpha times. And what does that mean? That's the one missing piece that we need to fill in that's a little subtle. So what would it mean to double a function gadget number of times? Okay. Well, so let's first figure out what the rules are for the phi. We'll resolve this in a little bit. But the standard rule is, of course, we base it with this. That's everything starts with successor. Basically, everything resolves down to successors at the base level. And we define it recursively, and it's simply, it looks formally easy until you actually stare at it for a minute. It's if you're already pretty confident with the kth version of the phi1 function, like maybe you're good with successor, and maybe you really understand doubling, even though these inputs are kind of new, these alphas are kind of new, and then you want to understand the phi1 with a 2 control argument. It says that phi1 with a 2 control argument is just repeat phi1 with a 1 control argument. And so this is almost verbatim what we had for f of k plus 1 comma n. But there it is again. It seems like to emulate what we had with the usual fast-growing hierarchy, you take whatever that input is and you just put it in the iteration slot, that exponent. Well, what the heck does that mean to iterate it an alpha number of times? It's actually not hard to unpack that. Okay, so if alpha is just a number, we know what it means. It just means if alpha is 7, this means do this previous operation 7 times. Just phi1 of k of phi1 k of phi1 k of, etc., etc. Okay, so that's not too hard. But what happens when alpha is a function? It's really quite simple. And we'll see that I've sort of snuck it in when I can hopefully convince you that doubling was a reasonable definition, like omega naught times 2. If you believe that, I was actually sneaking this concept in. Okay, so in a minute, another easy one to deal with is alpha is not a function, but is a successor of a function, or a successor of a successor. It's got some successor marks. That's actually going to be very easy to deal with. So I want to really get at the nub of what's weird and new about this is what happens when alpha is a function. Okay, so here's the deal. What kind of gadgets are the inputs and what kind of gadget is the output of this? Alpha's, in this case, we're thinking where alpha is a function. It's not a number. It's a more interesting thing. It's a gadget that eats numbers and spits out stuff. And it makes sense that probably what we're outputting is another function. So let me page up a little bit, right? Again, omega naught 2 is really the first example of this. Omega naught 2 was not a number. Omega naught's not a number, so we don't expect omega naught 2 to be simpler. It's the same kind of thing. It's a function. And what did I do? I defined what it did with a certain input. And I defined it to be omega naught plus k. Okay, so that seems maybe too simple as a base, but it really is the right idea. Okay, so we just need to know, let's go back. We need to know what is this previous function iterated alpha times on alpha. I just need to tell you what it does on a natural number input. In other words, this is how you define any function pretty much. Tell me what it does for an arbitrary input. And here's going to be the definition. And in the next video, I'll zoom out even a little bit more and say this is a really general concept. So we're going to say, here's the new gadget we're trying to make. We have alpha, and we're trying to create a massively bigger thing than that using some sort of fancy version of iteration of the phi1k function. And it just says what it means to iterate that alpha times and then resolve that with a k input is you just pass the k input to the iteration exponent. That's it. And so it's just parenthesis pushing. Just take this k and put it into that k input right there. Oh, shoot, I shouldn't use a k here. These are not supposed to be the same letter. Let's say that's an L. There's no relation with these guys. This is just some function, and it's a k being put into it. So sorry, that was a little misleading to think that the k's were different or the same. Okay, that's fixed now. All right. So yeah, let me cut it off right here. And say this is going to be there's very few more pieces of the puzzle that we have to put together. This is going to supercharge this off to incredible heights. And this is one of the most unfamiliar things. This is a version of transfinite iteration. Again, you really don't have to think about infinities of any kind here. It just doesn't have to come in. It's just sort of iteration where the objects can be functions. Pretty funky.